All right, today I'm going to show you guys how to do Lewis dot structures and how to put molecules together. And the first thing you have to understand with Lewis dot structure, the number of dots you have around an element is the number of valence electrons that that element has. And so that's what each dot represents, it's its valence electron. So when you talk about the number of valence electrons that potassium has, you look it up on the periodic table, potassium is in column 1 on the table, so it has 1 valence electron. So you would represent that 1 dot for the valence electron that potassium has. Carbon's in column 4 on the periodic table, and so it would have 4 dots. You put 1 in each corner, look at it as like a 4-sided structure, because you would actually, if you filled it up with 8 electrons, you'd put 2 on each side, because they do actually remain paired in orbitals when they are around an element. And then sulfur's in column 6 dots around it, so 1, 2, 3, 4, 5, 6, and fluorine's in column 7, so there would be 7 dots around it. Doesn't matter what point you start there, whether it's the top, the bottom, the side, but that's how you do dots. That's how you do valence electrons to make dot structures. So what we're going to show you is how to know the number of bonds and the number of lone pair electrons, the ones that are not in bonds around an element. And you use this formula, S equals N minus A. Again, I'm going to change the way I list this, because when I'm having you do go formative, I'm going to list it, it's the same way, but I'm going to N minus A will equals S. So the question is, what does that mean? N is the number of electrons that are needed, and that's a simple thing. We go, how many electrons would all the elements need? They would all like 8. There are some exceptions to that. They're listed right here. Hydrogen, remember, doesn't have any p orbitals in its outer shell, so it's just got an s orbital and it can only hold 2 total electrons in it, so it's 2. But there are also 2 other ones. Beryllium only needs 4, boron needs 6, and all the other ones need 8. So it's a very important thing to know when you talk about how many they need. Available electrons are their valence electrons. So we can determine how many they all have available by where they're at on the periodic table. If they're in column 7, they have 7 available. If they're in column 1, they have 1 available. So that's how we get that number. So when you take the total needed electrons and subtract the number they have available, that will actually get you the number. S is the number of shared electrons. So it gives you the number of shared electrons. And if you divide all of that by 2, what that'll do is that will get you the number of bonds, because a bond is an area between 2 elements that holds 2 electrons in it. That's why we divide it by 2. So what we use this for is determine how many bonds are in a dot structure. A long time ago, we used to just start shuffling these dots around to make the proper dot structure. Using this equation actually makes things much easier. And I'm going to do several for you now, and after you do a few of these on your own, you'll see why the equation makes things a lot easier. So a couple other things, when you're determining what the central atom is, if you have a question, a lot of times it's whatever you have the fewest of, whatever is the most metallic. And so again, those are some things to consider when you're talking about what the central atom is, but again, I'll explain further later. So again, let me show you real quick how to do dot structures for all of these, and then you can do some on your own. So first of all, you have F2, so you write down the symbols for each element there. What we're going to do is we're going to put needed electrons here, available down here. It's just a good way to keep track of everything, to know how many bonds we're going to have. And so first of all, needed electrons, remember, they all need 8 except for hydrogen, beryllium, and boron. So fluorine's not in that group. Each fluorine needs 8 electrons each, so that's a total of 16. Available, fluorine again is in column 7. It's got 7 valence electrons. There it is. So each one's got 7 available. So remember, so it's needed minus, again, so the equation is every time it's needed minus available equals shared electrons, and then divide that by 2, and that will get you the number of bonds. Again, a bond is a place where electrons, in this case, are being shared between 2 nonmetals. These are all covalent or molecular compounds here. So 16, so what we have there is then needed is 16, available is 14, so that is 2. And then again, we divide that by 2, and we have 1 bond here. So again, what you do when you're doing these dot structures is A bond is a line between two elements. Now I'm going to make it look like a barbell right now so you understand that a line represents a bond between two elements, and the bond represents an electron being shared by each of those elements there. So this fluorine is sharing an electron there, this one's sharing an electron, and the reason they're sharing them is so now that they can have a full outer shell, or an octet, or 8. That's why all the elements combine the way they do. They're trying to get 8 in their outer shell. When you use this formula, you determine number of bonds, and then all you have to do after that is go back and add dots around each element so that they would then have 8, unless they are an exception to the octet rule. So right now, they both think they have 2. They're sharing, but they both think they have them. So this fluorine thinks it has 2, that one thinks it has 2. So now I need to add dots until they have 8. So put 2 dots there, 2 dots there, and 2 there. And so now this fluorine thinks it has 1, 2, 3, 4, 5, 6, 7, 8. Again, they're sharing both of them. They both think they have those 2. They're sharing them so that they have an octet. And then this one has, fill in the dots, and now it thinks it has 8 as well. So again, this one thinks it has 8. This one thinks it has 8. And now there's the dot structure that holds fluorine together. That's called a single covalent bond. Covalent sharing between nonmetals. Single bond means it's just one dash. Now, you don't have to make the dashes with barbells, with the dots on the end of them. I'm just showing you that that's what that dash represents. So anytime you see a dash between two elements, it represents just a regular bond where each element is sharing an electron. The toughest part of this is checking them when you're done. So what you have to do is check to make sure they both have electrons to put in that bond, because sometimes you can have each of the 2 electrons come from the same element. It's called a coordinate bond, and the only way you can ever find a coordinate bond is by checking to make sure they each have their number of electrons to put in that bond. So you use this number at the bottom to check it. So this fluorine's got 7 electrons to share. 1, 2, 3, 4, 5, 6. Okay, obviously those belong to that fluorine because they're not even in the bond. These are called lone pairs. And then there is its 7th electron right there, and so it works out great. You got to check it with the other one. This one has 7 to share. Does it have 1 to put in that bond? That's what we're checking for. Does it have an electron put there? 1, 2, 3, 4, 5, 6. Obviously, they belong to this fluorine. They're not even in the bond, and there's its 7th one, so it works. That's called a single covalent bond. Again, you check them because you're looking for what's called a coordinate bond, which we'll get to in a minute. All right. O2, needed, available, and all right, so number needed there is 8 apiece. Number available, in this case, oxygen's in column 6. So I got 6 apiece. You're going to wonder where I'm getting these numbers. It's in column 6 there. And so it's got 6 electrons each. So in this case, it would be 16 minus 12 is 4. And then remember, divided by 2 will get you bonds. So it's got 2 bonds. And so this is, like I say, this is much easier than what we used to do a long time ago to try to shuffle all these electrons around and figure out how many bonds they have. Because what we're trying to do is make sure they all had 8. So what this is telling us is this is going to make 2 bonds. That's called a double covalent bond. Again, I'll make them look like barbells right now to make sure you understand now that that represents sharing of 4 total electrons, 1, 2, 3, 4. So that's a double covalent bond. 4 total electrons are being shared between them. Then all you have to do is go back and add dots until they all have 8. Now remember, they both think they have those 4. So they're sharing those 4. So this one thinks that's 4. So there's 5, 6, 7, 8. And then this one over here, 5, 6, 7, 8. Again, so now, this one has 8 electrons. This one thinks it has 8. So 1, 2, 3, 4, 5, 6, 7, 8. I count them, all 4 of them in there because they're sharing both of them. They both think they have them. So now they have 8 in their outer shell. So you figure out how many bonds you have, add dots until they both have 8. Then you got to check to make sure it actually has electrons to put in those bonds. And oxygen has 6 to share, 1, 2, 3, 4. I count those 4 belong to that oxygen because obviously they don't belong to this one because they're not even in the bond. And then there is 5 and there's 6. And so this one has 6 to share. It works out great. The other one, 1, 2, 3, 4, 5, 6, works great. That's called a double covalent bond. And in a double covalent bond, they're sharing 4 electrons between the 2 of them. All right, the next one, again, needed electrons here, available here. We got nitrogen and 8 and 8. Number available, nitrogen's in column 5 on the periodic table. It's got 5. So that would be 16 minus 10 is 6. Divided by 2 will give us bonds. There's 3 bonds between them. You see how fast it is. You know, if you get working on these after a while, you get really good at them. And so now that they're sharing, that's called a triple covalent bond. And the more bonds you have between them, the closer they're held together, so the stronger that bond is. And so that's a total of 6 electrons being shared. Now, they both think they have those 6. They're sharing them together. All I have to do is add dots until they have 8. So now that one has 8. This one has 8. Again, they're sharing those 2 between them. So now they have 8 electrons. You got to check that, you know, they have 5 available to share. You're checking to make sure they have 5 to put in that bond. 1, 2, 3, 4, 5. So that works. This one has 5 to share. 1, 2, 3, 4, 5. Works. Again, triple covalent bond. All right, CO2. Try to keep them symmetrical. In other words, you have CO2, put carbon in the middle. A lot of times, whatever you have the fewest of will go in the middle. Everything else on the outside. Again, we'll try to keep symmetry there. So needed electrons goes here, available there. They all need 8. Remember, the exceptions are hydrogen, beryllium, and boron, and that's none of those. So available, again, you got to check each one of them. So oxygen's in column 6, but carbon's in column 4. So this has 6 available, this has 4 available, and this has 6. So multiply those together, that's 8 times 3 is 24. And then minus 16 is 8, and 8 divided by 2. That would be 4 bonds there between the 2 of them. And so, you know, what we're going to do is, well, we got 4 bonds we need to put between them. We're going to put 2 there and 2 there. Doesn't always work that way, but that's, you know, you start off doing what the common sense thing would be to do. Then you just start adding dots until they all have 8. Remember, these lines represent electrons, so each line represents 2 electrons. And so right now, this oxygen on the end is sharing 4 electrons with carbon. Remember, you add dots so that they have 8. So if it's already got 4 in that bond, there's 5, 6, 7, 8. You're not adding dots to equal this number at the bottom. You're adding dots so they all have 8. Carbon in the middle is sharing electrons on both sides. Remember, there's 1, 2, 3, 4, 5, 6, 7, 8. It thinks there's 8 already. Doesn't need any dots around it. And then the oxygen at the end thinks that's 4, so 5, 6, 7, 8. And again, that's the way they're sharing them. So that oxygen thinks it has 8. Carbon in the middle thinks it has 8. This oxygen over here thinks it has 8. You check them with the number available. So this has 6 available. 1, 2, 3, 4, 5, 6. Works. Carbon's got 4 available to share. 1, 2, 3, 4. This has 6 to share. 1, 2, 3, 4, 5, 6. It works. All right. Next one. Hydrogen and oxygen. Needed, available. Hydrogen is an exception to how many they need. Hydrogen only needs 2. So 2 there, 8 there, and 2 there. Available, hydrogen's in column 1, oxygen's in column 6, and hydrogen, again, is in column 1. So that's 12. So that's 12 minus 8 is 4 divided by 2. There will be 2 bonds there. 1 there, 1 there. Then I don't need to add any dots to hydrogen because remember, hydrogen doesn't need 8. It only needs 2. But the oxygen in the middle right now thinks it has 2, you know, a bond there and a bond there is total 4 electrons. So 5, 6, 7, 8, because it does need 8 in its outer shell to be happy. And then you're checking to make sure this works. There's the one that hydrogen has to share. Does oxygen have electrons to put in those bonds? 1, 2, 3, 4, there's 5, and there's 6. Hydrogen works, and so it works from there. The next one, carbons, hydrogens. Now in this case, put the carbons in the middle. You're going to put the hydrogens on the outside. You never try to link like a carbon, a hydrogen, and another hydrogen, because hydrogen only can make 1 bond. So hydrogen always has to go on the perimeter. It can't make more than 1 bond. So when you talk about how many they need, 8, 8, 16, 18, 20, 22, 24. That's how many that are needed there. Available, 4, 4 is 8, 9, 10, 11, 12. So 24 minus 12 is 12. 12 divided by 2, 6 bonds there. 1, 2, 3, 4, 5. There's the 6th. Now I can't put a double bond on a hydrogen because you can only have 2 electrons, and the bond represents 2 electrons. When you look and check them to see, well, the carbon has 4 to share. Does this work? 1, 2, 3, 4. Remember also, does carbon need any dots here? 2, 4, 6, 8. Doesn't need any because it thinks it already has 8 electrons. That carbon on that side does as well. All right. Now I keep telling you how to check them, but you haven't seen any that didn't check out properly. So now we're going to come up against one of those. It doesn't check, and you're going to find what's called a coordinate bond. So needed again, 8 and 8. Available, 4 and 6. That is 16 minus 10 is 6 divided by 2. There's 3 bonds between the two of them. 1, 2, 3. Then you add dots until so they've had 6 electrons between the two. They both think they have them. They're sharing them. You got to put 2 dots there to make carbon have 8. Got to put 2 dots over here to make oxygen have 8. Then when you check them is when you got a problem. Carbon's got 4 to share. There's 1, 2, 3, and 4. It doesn't actually have an electron to put in that bond, but when you check the other element, you will see where that electron comes from. Oxygen has 6 to share. So there's 1, 2, 3, 4, 5. The 6th one came from that oxygen. So there is its 6th electron right there. So that arrow means that's called a coordinate bond. And a coordinate bond by definition is a bond where both electrons come from the same element. That's what a coordinate bond is. You identify that with an arrow, and it is pointing away from the element that's donating those two. So this one, there's its first, second, there's its third, there's its fourth, there's its 5th electron, and there's its 6th. And I have so many people over the years that are like, I don't understand how you know that came from oxygen. Well, because it couldn't have come from carbon, because carbon's got 1, 2, 3, 4 to share. That's all it had available to share. So this extra electron here had to come from oxygen. So again, I'm telling you, well, they both came from oxygen, but they're being shared between the two elements? Yes, that's what a coordinate bond is. You identify it with an arrow. All right, moving on to the next one. You got O3, which is ozone. So O3 there, needed, available. So it's 8 apiece. They're in column 6. So that is 24 minus 18 is 6 divided by 2. There'll be 3 bonds. You're going to put 2 there. Now again, so what, a lot of people are creative, try to go make a triangle out of them to equally represent one bond connected to each one. But in reality, this molecule is a linear molecule. So you just put 2 on one side, 1 on the other. It's got to pick. When you have 3 bonds to place there. Then you start adding dots until they all have 8. This one right now, each line represents 2 electrons, so there's a total of 4 there that this one thinks it has. And so I'm adding dots until it has 8 electrons there. The oxygen in the middle, 2, 4, 6. Going to put 2 dots there. Now it's got 8. The one at the end's only got 2 electrons in that bond, so 3, 4, 5, 6, 7, 8. When you check it, you have a problem again. Check to see that you're checking for a coordinate bond. This one has 6 electrons to share. 1, 2, 3, 4, 5, 6. It works. This one has 6 to share. 1, 2, 3, 4, 5. That means that this one, there's its 6th electron over there in that bond. Now that also means that the one at the end, it only has 6 to share, and it can't have one in that bond. And look, there are its 6 dots right there. It does not have one in that bond to share. So again, that's called a coordinate bond. And what does it mean? It means just both of those electrons came from the oxygen in the middle. That's what it means. So that's what a coordinate covalent bond is. All right, now we're going to do polyatomic ions. So again, we put whatever we have the fewest of in the middle, surrounded by everything else. Try to make it symmetrical. When you do needed electrons, so needed electrons, that would be 8 times 5, because there are not exceptions there. So that'd be 40. Available electrons, they're all, sulfur and oxygen, again, are all in column 6. So that would be 6 times 5, which is 30. But again, this thing has a -2 charge, which means it has 2 extra electrons. And what that's going to do is that's going to affect that number. So it has 2 more electrons than you would normally think it would have available. So you're going to change that. You're going to add 2 electrons to it because it has a -2 charge. So instead of 40 minus 30, it's 40 minus 32, which is 8. And then 8 divided by 2, it's got 4 bonds there. Okay. 1, 2, 3, 4. Add dots until they both have 8. When you guys are doing these on GoFormative, you got to make sure we can see these dots, because you can do that. You can draw on GoFormative, but we got to be able to see the dots to count it correct. And but when you're dealing with a polyatomic ion, a group of atoms with a charge, you do not have to check for coordinate bonds. And the reason is actually, since you can put these 2 extra electrons wherever you want, it can be drawn more than one way. Because right now, if you're checking it going, wait a second, sulfur's only got 6 to share, but there's 2, 4, 6. Where did these 2 come from? It's the extra 2. And so you can put those extra 2 wherever you want to put them, though. And so it can be drawn more than one way. So you don't have to check them if they're polyatomic ions. And then you got NH4. So there you go. Put the hydrogens around the outside. But here, though, when we go needed, there's 8 for nitrogen in the middle, and then 2, 2, 2, and 2 for hydrogens on the outside. So that's needed. Available here would be 5, and then 1, 1, 1, and 1 for the hydrogens because they're in column 1. So, right, that's 10, 12, 14, right, let's see, we got 16, and then 16, and there's 9. But again, the whole thing is plus 1 because it's got a charge, and it affects the number available. So instead of having 9 available, it only has 8 available because this plus 1 is lost an electron, it's given it to something else. 16 minus 8 is 8, 8 divided by 2, 4 bonds, 1, 2, 3, 4, and you're done there. And again, you don't have to check it because it's a polyatomic ion. There are some exceptions to the octet rule. I'll just leave it here. Some things have more than an octet. PCl5 is one of them. Sulfur can make 6 bonds around it and have more than 8. Again, there are always exceptions to this. Don't worry about them right now. I'm going to revisit these later with the next lesson. But we'll do these last two and we'll finish up. So BF3, and so we're going to do that. And so needed electrons would be for fluorines 8, 8, and 8. And boron is one of the exceptions. Boron only needs 6. And so available electrons, again, it's based off what column they're in. Fluorine 7, 7, and 7. Boron's in column 3. So it's got 3 available. So let's see, what is that? So 6, 24, there's 30 minus 24 is 6. 6 divided by 2, 3 bonds. There's 3 bonds. Add dots until they all have 8. But we got a problem here. Boron is an exception. Boron does not need 8 electrons. It only needs 6. So we don't need any dots there. So it's 2, 4, 6. It's happy that way. It's very important that you understand not to put those dots there for boron because they actually take up space and they change the shape of that molecule, which is what we're going to talk about next time. And then beryllium and chlorine. So it's beryllium. Needed electrons again. Chlorine 8, but beryllium is another exception and only needs 4. You're just going to have to remember that. Boron, beryllium, and hydrogen do not need 8. Available electrons, these are in column 7. Beryllium is actually in column 2. So again, that's 20 minus 16 is 4 divided by 2. There's 2 bonds there, 1 there and 1 there. Add dots to the chlorine. Add dots to the chlorine until they both have 8. But again, boron right now thinks it has 4 in its outer shell. It doesn't need any dots around it because it's happy with 4. So you'll have some of these to work on and go formative. And then next time I'll show you how to start building molecules and understanding the shapes of the molecules. Good luck.